One of the most interesting parts of machine learning is generative machine learning. In this video, we're going to be using that exact technique, specifically a generative adversarial neural network, to get started with generative machine learning. Let's do it. So in this video, we're going to be covering a bunch of stuff, but specifically we are going to be focusing on generative machine learning using a generative adversarial neural network. Now we're going to be using this to build and design our very own fashion line, but this could be just about anything. You could generate synthetic images of a whole range of different types of fields or spheres or objects, who knows. Now, we're going to take this step by step and code it up all the way from scratch. So this is going to be installing our dependencies, getting our data, visualizing our data. Then we're going to get to the good bit. And this is where we actually build our generator model. So this is the actual neural component that is able to generate new images or new objects. We'll then take it a little bit further and design our discriminator model. Think of this as an art critic, which is trying to detect a fake from a real image. And we'll wrap it all up in a custom training loop and then visualize our results. Ready to do it? Let's get to it. Hey Nick, what are some use cases for GANs? Well, basic GANs are great at generating synthetic data. More advanced models allow you to do things like super resolution, smoke removal, and style transfer. Sweet. Think you could build us a simple GAN to maybe generate some fashion? Sure, let's get to it. First thing we need to do is set up our environment. Welcome on back to the breakdown board. I really wanted to do that. It's been a while. Okay, so in this video, we're gonna be building a GAN, but not just any GAN. We're gonna be building GAN to generate fashion. So the first thing that we're gonna be needing to do is get some images of fashion. Now, in order to do that, we're gonna leverage the TensorFlow dataset API, AKA TFDS. And we are specifically going to be using the fashion MNIST dataset. So this is going to allow us to get images of things like t-shirts, shoes, let's draw a boot or something, and things like bags as well. So like it's got a whole bunch of random images that we can actually use for our particular dataset. So the thing that we're then going to do is we're actually going to have to build up a generator. So a generator is going to take in a bunch of random numbers, and this is commonly referred to as a latent dimension. So it might be like 1, 23, 42, 71, so on. And what that is actually going to output is it's going to take in those random numbers and it's going to output a set of values which represent an image. So what we're actually going to do, so let's say for example, the images that we're getting back from TFDS are going to be in the shape 28 by 28 by 1. We might take in some random values into our generator. Let's say in our particular case, we'll take in 128 random values. Those 128 values will be reshaped into a format that allows us to output a set of values which are 28 by 28 by 1. So we'll actually take those 128 values and we'll build up our generator. So our generator will be comprised of a number of convolutional neural network layers, as well as some upsampling layers. And eventually what we are going to get, probably connect these, hey? We're going to output an image which is 28 by 28 by 1, which is effectively a generated image. That is the crux of a GAN. Now, this is where the discriminator comes in. We'll actually take the generated image and pass it through a discriminated neural network. And that is again going to have a number of convolutional neural network layers. But the final output for that neural network is going to be a 0 or a 1, which represents whether or not it's a true or a fake image. So we've set it up so that 0 represents true and 1 represents fake. Now, other implementations might do this a little bit differently, but this is definitely going to work. So we'll then take that generated image and bang it into our discriminator. At the same time, we'll also take real images, all the way from TFDS. Let's just make an entry. So one will be going here. So that will come from our TFDS model, and we'll be able to train our discriminator as to what is real and what is true. Now this is where the fun bit comes in, the custom training loop. I've drawn some dude lifting weights here, but you kind of get the idea. We actually need to balance off the training between our generator and our discriminator. And this is a key step when it comes to actually building GANs. We actually train our discriminator, and it gets rewarded if it effectively picks out fakes. Whereas our generator gets rewarded if it's able to fool the discriminator. So generator, its goal is to fool the discriminator. Now the cool thing about Keras and TensorFlow, which is going to be the deep learning framework that we're actually going to use, is that we can actually create a custom train step. And through here, we can actually build that custom training loop, which allows us to build a generator. Now, finally, when it comes to actually testing this model, we can actually take the generator model specifically, discard the discriminator because we don't really need it anymore. It's purely needed for training. We can then pass through those 128 random variables to our generator. Let's say that this is our generator is represented as a pink model, gen mod. And then what that is going to do is it's going to output our different images of fashion. So we might get a t-shirt, we might get a boot, so on and so forth. Now there's a whole bunch of applications for this. Again, you can use it for generating other types of stuff. You can even go to a slightly more advanced model called a conditional GAN, which gives you a little bit more control as to what it is that you actually generate. For now, we're going to keep it simple. Let's get to it.
Alrighty, so the first thing that we told our client that we were going to do in order to build up our GAN is set up our environment. Now, in order to go through and complete our GAN, there's a bunch of stuff that we're going to do, but we'll set up our environment first. So once we've done that, we're going to visualize and build our data set. We're going to take a look at building our neural network. So we'll build up our generator, our discriminator, which I'll talk about more later. And then we're going to construct our training loop, which is pretty involved, but we'll walk through it and then we'll test out our generator. But first things first, let's go on ahead and set up our environment. Now, the first thing that we need to do is install some dependencies. So the main dependencies that we're going to have around here are TensorFlow, Matplotlib. So let's go on ahead and install those, and then we'll be able to kick things off. Okay, so those are all of our dependencies that we're going to need. So I've written one line of code there, and the full line is !pip install TensorFlow, TensorFlow-GPU, Matplotlib, TensorFlow-datasets, and IPyWidget. So TensorFlow and TensorFlow GPU are going to be the core dependencies that we're going to need to actually build up our deep neural network. Matplotlib is largely going to be used in the visualization component. So when we actually go and visualize our data sets in the next step, after we've had a chat to our client, we're going to be using that. TensorFlow datasets is the actual data set that we're actually going to be using. So if you go to TensorFlow datasets and actually take a look, so there's a bunch of data sets available. Now we're just going to be using the fashion data set. So I think we can go into the catalog and search for fashion. I think it's in here. Yeah, so we're going to be using fashion MNIST. So there's a bunch of images from Zalando's article images. So they're all 28 by 28 grayscale. So this is just going to make building our deep neural network a little bit faster rather than using monster images like I've done for the super resolution tutorial, which will be coming around kind of soonish. Cool. All right, so those are our data sets, and then IPyWidgets is just a dependency whenever you're downloading TensorFlow data sets. So if we go and run that, I'm pretty sure I've got all of these installed already, so it should run relatively quickly. And it has, let's double check, we've got no errors. So we've got a warning saying we need to upgrade pip. That's perfectly fine. We can ignore that. Now, I always get the comments, Nick, show us what versions you're using. So I'm just going to run a quick pip list and show you what versions of stuff I'm using. So the core things that we need to take a look at are TensorFlow. So over here, you can see I'm using TensorFlow 2.8.0 and TensorFlow GPU 2.8.0. TensorFlow datasets, we're using 4.5.2. What else did we have? We installed Matplotlib. Let's take a look at that. Matplotlib, we're using 3.5.1. So that should hopefully get you across the board if you're trying to work out what versions of stuff to install. Keep in mind that the versions of TensorFlow that I'm using are namely because I'm matching the version of CUDA and CUDNN that I've got installed. So I've probably shown this a billion times, but I want to show you just once more. So if you actually type in TensorFlow GPU into Google and you actually take a look at use GPU, there should be, I'm not sure if it's on this page, but there's actually no, it's not on this page. So there's actually a compatibility guide. Here we go, it's down here. So over here on the left-hand side, build from source actually shows you. So if you scroll all the way down, this actually gives you the configurations that you're gonna need. So I'm using 2.8, 2.9 is now out. So I'm using 2.8, which means that I need to have, and I'm running this on Windows, which means that I need to have Microsoft Visual Studio Code 2019, Bazel 4.2.1, and then these are the two most important bits in order to enable GPU acceleration. We need CUDNN 8.1 and CUDA 11.2, not optional, you need both. Just key thing to keep in mind as to why I use specific versions. Okay, so that is our set of dependencies now installed. The next thing that we need to do is, first up, what we are going to do is limit the GPU consumption. So if I actually show you my little GPU at the moment, so right now you can see that we've kind of spun up some stuff, so we might need to shut down some existing kernels. But what we want to do is we want to limit the virtual RAM growth. And this is a key thing whenever you're using TensorFlow, it'll expand to use all of that RAM. So you want to constrain that a little bit so you don't get a ton of out of memory errors. So we can do this using the GPU. I think it's set memory growth equal to true. So I'm going to show you how to write this command and then we'll take a look. So let's do it. Okay, that is our memory growth now set. So we've gone and written 4 lines of code, and you've probably seen me bring this one in a ton of times before. So the first line that we've written is import TensorFlow as TF. So this is going to allow us to leverage TensorFlow. So bringing in TensorFlow. And then if you've ever watched any of my other deep learning tutorials, these 3 lines are going to be super common. So first up, we go and grab all of our GPUs, and the full line there is GPUs equals tf.config.experimental.list_physical_devices. And then we're going to pick up all of our GPUs. So if I actually type in GPUs, you can see I've only got one there. So I've got a 2070 Super on this deep learning machine. And then what we're doing is we are looping through each one of those. So if we actually did have multiple, then we'd actually go and loop through every single one of them. This just sort of sets you up for scaling if you were to use multiple GPUs later on. So the next line is for GPU in GPU. So it's effectively looping through this. So for GPU in GPUs, print GPU. So you can see it's going to print out each physical device. Then we're actually setting that memory growth. So remember, I sort of mentioned that function. So tf.config.experimental.set_memory_growth. We're passing our GPU. So that particular GPU as part of our iterator, and we're setting that growth equal to true. So that means we're not going to blow out our VRAM when it comes to actually building up our deep neural network. Now, the last thing, or the second last thing that we need to do is actually import the rest of our dependencies. So we've so far installed a bunch, we've taken a look at our versions, and we've limited our memory growth. We now need to bring in the rest of our dependencies and then bring in our data. So first up, let's bring in the rest of our dependencies. Okay, those are our next 2 dependencies now brought in. So I've gone and written 2 lines there. So the first thing that we're doing is bringing in TensorFlow datasets for fashion mnist. So that line there is import TensorFlow underscore datasets as TFDS. So this is going to allow us to use this fashion mnist dataset. And so we're going to effectively be able to generate images that kind of look like this, which could be scaled out to be able to generate color images, could be scaled out to generate bigger images. There's a ton of stuff that you could do. So we are bringing in TensorFlow datasets, and then the next line that we're bringing in is bringing in matplotlib for viz stuff. So the line there is from matplotlib import pyplot as plt. So really just 2 core lines of code there to bring in our dependencies. Now the next thing that we need to do is actually download and import our data set. So let's actually do that. Okay, and that is our data set now loaded. So we've actually gone and used the TensorFlow datasets API. So use the TensorFlow datasets API to bring in the data source. So we've written one line of code there. So it's ds equals tfds.load. So you can see that there. So tfds.load. And then we've specified what data set we actually want to bring in, which in this case is fashion MNIST. So it's this one over here. And the cool thing about the TensorFlow datasets catalog is that you can kind of just reference it as that and bring in a ton of different types of datasets. And I think I've talked a little bit about how to work with the TensorFlow dataset API previously, not getting it from the TensorFlow datasets, but building your own. But this is how we go and download a pre-existing one. So tfds.load is your friend, and then you pass through which dataset you want. So let's say, for example, you wanted, I don't know, images of satellites. You could actually pass through Eurosat and you would get satellite images. It doesn't actually show it there, but that's sort of the cool idea behind it, that you can iterate really quick. And then we specify that we only want the training partition. So we've specified split equals train. So the full line is ds equals tfds.load, and then we're passing through fashion MNIST as the first positional argument, which is just a string, and then we're passing through a keyword argument, so split equals train. So we now actually have our data set. So if we actually went and took a look, so ds.as numpy iterator, let's take a look at the type first. Okay, so this, if we take a look, this looks like it's a prefetch component, so it's part of our TensorFlow datasets API. So if we went and typed in as numpy iterator next, we should be able to get a array. There you go. So what we're actually getting back is a dictionary. So you can see the first component is the image itself, and then if we scroll on down, let's actually take a look at the keys. So we've got an image and then we've got a label. So if we actually went and grabbed the image, right? So this is just an image. So we're actually going to take a look at how to visualize this in a sec, but just know for now that we've got an image, and this is obviously a classification data set, so we can take a look at the labels as well in that particular case. Alrighty, that is the first component now done. So we've now gone and imported our dependencies in our data. So remember, we went and installed a bunch of stuff, specifically TensorFlow, TensorFlow GPU, Matplotlib, TensorFlow datasets, and IPy widgets. We then went and limited our memory growth. We went and brought in a couple of dependencies to TensorFlow datasets and Matplotlib. And then we went and downloaded our dataset that we're going to use for our GAN from the TensorFlow datasets catalog. And we're bringing fashion MNISTs to be able to generate our own fashion components. And then we also took a look at briefly look at our dataset, but we're going to dive into that a bit more in a second. All right, let's jump back on over to our client and have a chat.
So that's all done? It's done. Well, what next? It's always good practice to visualize our data. In this case, we've got some pretty small images because it's just a prototype, but it's still worthwhile taking a look with Matplotlib nonetheless.
So as I mentioned, it's good practice to visualize your dataset before you try to do anything with it, because otherwise you're sort of just walking in the dark, which can be a little bit problematic when you're building machine learning things. So what we're going to do now is we're actually going to take a look and visualize our data set. Now, in order to do that, first thing that we're going to do is bring in NumPy. So import NumPy as NP. And we're specifically going to use NumPy to do some data transformation, which we'll see in a second. So now that we've actually gone and grabbed or brought in NumPy, the next thing that we actually want to do is build an iterator. So you would have seen here before, I was actually creating a loop to be able to continuously grab data out of our TensorFlow datasets pipeline. So what we've actually got here, so by downloading our TensorFlow or fashion MNIST dataset using the TensorFlow dataset source, we've actually got a pipeline. Don't think of it as you've loaded in all of your images into memory. We've got a set of repeatable calls that we can make to this pipeline to bring data back, right? Now, in order to bring that data back, we first up need to actually set up an iterator. So think of this like almost like a connection, right? We can then call next to bring back the next batch of data. So by setting up the iterator and then going next, it'll bring back one batch or one image, depending on how big the batch size is. Then if we go next again and bring back another one, next again, it'll continuously bring back more data. So what we're going to do is first up set up an iterator, which is effectively just going to look like this, right? And we're going to call it data iterator. Setup, let's call it connection. Setup connection, aka iterator. So then what we can actually do is just call the iterator and type in .next, and this will continuously bring back a batch. Traditionally, you'll batch up the data set so that you've actually got multiple images per batch or multiple samples per batch. So if we type in data iterator.next, so you can see that that's one image. Then if I call another one, that's actually another image. So watch these numbers down here, right? They're actually going to change. So you can see that that changed. So we're actually bringing back new data sets each and every time. Boom, 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 boom. So what we're actually doing is we're calling out to that pipeline and bringing back a new batch every single time. So it's not loading it all into memory to begin with. It's actually making a call and bringing back data as and when we need. So this helps preserve some of the memory on your computer, particularly when you're doing hardcore deep learning. Okay, so now that we've taken a look at how to get data out of a pipeline, so getting data out of the pipeline. Boom. All right. And then we can, cool thing about JupyterLab, I don't know if you've seen this, is that if you actually right click on an output cell, you can actually enable scrolling for output. So then rather than me having to go all the way down to find the next cell or go to the next bit, it actually allows me to condense the output. So if I enable scrolling for outputs, you can see that much cleaner now. So I can actually see what the hell I'm doing. Hopefully that makes your life a little bit easier as well. Okay, so what have we done? Brought in NumPy, set up our iterator, aka our data connection, and then I've shown you how to get data out of the pipeline. The next thing that we actually want to do is do a little bit of viz. So the first thing that we're going to do is create some subplots. So we're going to use plot.subplots to actually create some subplots using matplotlib, and then we'll plot out 4 images. So let's do it. Okay, there we go. So we've actually gone and visualized some of our images now. So let's take this step by step and let me show you what I've actually written there. So I've written 5 different lines of code. So the first line is actually establishing think of the way the matplotlib is almost like setting up the format and then you plugging in images, particularly when you're working with subplots. So first thing that we're doing is we're setting up the format. So set up the subplot formatting. And all we're really saying here is that we want 4 columns and we want the total figure, which is the total plot, to be 20 by 20 pixels in terms of size. So then the entire figure is referenced as figure. So this is the fig is actually the whole thing. AX is each one of these individual subplots, right? So AX could just as easily be called subplot 1, subplot 2, subplot 3. So if we actually take a look at AX, right? It's just 4 different components. So that's the first subplot, that's the second subplot, that's the third, that is the 4th, right? And then we can actually visualize something in each one of those individual little subplots, which is exactly what we've done. So first thing we're doing is we're setting up the subplots, and the return values that we're going to get back are the entire plot, the whole thing, and the axes, which is 1, 2, 3, 4, because we've specified n cols equals to 4. Then we're looping 4 times. So we're going and grabbing 4 individual images from our data iterator, which is over here. So we're just calling .next 4 times, which is exactly this. So for IDX in range, so let's say we're going to loop 4 times and get images. So for IDX in range 4, first thing that we're going to do is we're going to get a batch. Now, a batch is effectively just a sample in this case. I could just as easily call this sample because it's not really, I don't believe it's been batched up, right? So we're getting one sample by calling data iterator.next. And remember that sample is going to be comprised of 2 parts, the image, which is part of a dictionary, and then the label. So the first thing that we're doing is we're using the axes, and we're using the ImShow function, which is just the image show function available inside of matplotlib. And then we're passing through our image. Now we're squeezing it because it's actually inside of a set of subarrays. So if we actually go and grab an image, .shape. So what we actually want to do is we want to condense this down. So we've got a single value down the bottom. So if we actually type in np.squeeze, get rid of that. So you can see that we're now collapsing it down. So if we type in .shape now, it's just 28 by 28, which allows us to visualize it a whole heap easier. Okay, so what are we doing? So we're first up getting the axes that we want to visualize. So we're going to grab the first index or the first axes. So let's actually take a look. So AX. So we're effectively going, all right, grab index 0. And then what we're going to do is we're going to type in .ImShow and then pass through the image, which is exactly what we've done there. So mp.squeeze, we're grabbing our sample image and then we're passing it to that. So that is what actually does the visualization. So let's actually write some comments. So grab an image and label, plot the image using a specific axis. Actually, we'll call it subplot. And then the next thing that we're doing is we're just setting the title. This is purely optional. Like if I commented that out, it'd just get rid of the numbers at the top. Now the numbers at the top are not all that descriptive because we haven't actually gone and taken a look at what each one of those labels are, but presumably label 5 is going to be some sort of high heel. Label 8 is going to be a bag. Label 6 is going to be a jumper because you can see those two there. So this is just printing out or appending the image label as the plot title. And to do that, we've written AX and then we're passing through the index. So we're grabbing this specific subplot at a point in time. And then we're using .title. So we're grabbing the .title attribute and we're using the .setText function to be able to set the text above that. So you can see those little 5s. Let me zoom in on that. So you can see that 5 there. You can see that 8 there, so on and so forth, right? So that makes it a little bit easier to see what we're actually plotting out. So again, we can keep plotting. We're going to see different images. So 4 might be a men's jumper, 5 might be a shoe, 1 might be some pants, 9 a boot, 4 a men's jumper, 9 a boot again, 3 a singlet or something like that. You sort of get the idea, right? So we can actually visualize each of those images. And because we're using the .next function, we can actually keep getting different sets of images back. Pretty cool, right? So we're getting a whole bunch of different images. So 4 men's jumper, 9 boot, 8 bag, 6, what is that? Singlet, jumper, whatever. You sort of get the idea. But we've got our fashion images. Now we're actually going to use our GAN to be able to generate these types of images. Now, if you think about the capabilities of this, we could actually use it to be able to generate synthetic data sets. We could use it to be able to generate faces later on, because all we'd really need to do is sub in different types of images and use a similar pipeline to do this type of thing. Okay, so that is our visualization now done. So far what we've gone and done is we've done a little bit of data transformation using NumPy, because remember we used np.squeeze to collapse our array. We've taken a look at how we can set up a connection to our data set, how we can go and get data out of the pipeline, and we've taken a look at how we can go in ahead and visualize it. And guys, as per usual, all this code is going to be available via GitHub, so I'll include the link in the description below. I'm just going to clean this up a bit. Alrighty, cool. Now the next thing that we actually need to do is do a little bit of data processing. So right now these images are represented as values between 0 and 255. In order to build good deep learning models, we typically want to scale values to be between 0 and 1. So we're actually going to set up a quick function that allows us to scale our images. So let's go on ahead and do that. Cool, so that is our function to scale our images. So scale and return images only. Now, we're actually going to transform our data pipeline so that it only returns the image. We don't actually need the label at the moment because it's not a supervised classification problem. If we were going to build a conditional GAN, which I might talk about in a future video, we might actually need those labels because we'd actually want to pass through what type of image we want to generate. For this particular model, we're just going to be generating different types. We're going to sample from the latent space to be able to generate different types of fashion. So let's take a look at our function first up. So first up, we've defined a new function and then we've set it equal to scale images. So that's going to be the name of it. And then that is going to take in the data from our TensorFlow data pipeline. We're then going to extract the image only, because remember the dictionary that we got back included the image and the label. We just need the image for this. So image equals data, and then we're grabbing it using the key image. We're then returning the image divided by 255. So this is going to scale our image to be between 0 and 1, hopefully to build a neural network that performs a little bit better and trains a little bit faster. Cool. All right, so that is that. Now what we need to do is actually apply that to our data pipeline. So if you've seen, what was it? I think it was actually the image classification video. You'll know that I remember how to do this by the initialism mexshabap. So remember, we need to map our data set. we need to cache it, we need to batch it. What is it? B, A, and then P, and then prefetch. So let's actually, oh wait, there's an S. We also need to shuffle it. So let's actually take a look at how to do this. So we'd actually go map, so, and then cache, and then S, which is shuffle, and then batch, and then prefetch. So these are the steps that you typically go, FETCH, there we go, that's how to spell prefetch. So these are the steps that we typically do whenever we're going and building up a data pipeline for TensorFlow. So that is exactly what we're going to go on ahead and do. So let's go and do it. Okay, that is our data set now prepared. So as I mentioned, we are going to run through the Mxshabat pipeline. So map, cache, shuffle, batch, and prefetch. So the first thing that we've gone and done is reloaded the data set. Completely optional. You could just as easily use the data set that we brought in from right up here. I've just gone and I like having it in a little condensed area. So ds equals tfds.load. And again, we're loading fashion mnis just so you get used to actually how to do that. We're grabbing the train partition. All right, then this is where the magic happens. So first thing that we're doing is we're running the data set through the scale images pre-processing step. And I really like the way that this works because we can actually take almost apply data pipelines, which is effectively what this is doing. So we're taking our data and we're running it through the scale images function. We could go and do other stuff. So if we wanted to do data augmentation, I've got a better idea of how to do that now. We could actually go and apply data augmentation step here as well. But now we don't actually need it. Then what we're doing is we're caching our data set. So cache the data set for that batch. We're then shuffling it. So this ensures that we've got a shuffle data set. So we're not just looking at a specific set of samples. So shuffle it up. And so actually, let me just quickly walk you through this. So first up, what we're doing is we're grabbing the data set that we defined up here, and then we're overriding that variable. So ds now equals ds.map, and we're returning it once it's being passed through the scale images function. We're then caching it. So we're taking ds, and then we're caching it. So by applying the cache function, so ds.cache, we're then shuffling it up. So again, we're grabbing the ds or the data set. We're then passing through or using the shuffle function, and we're specifying the value to that shuffle function as what the shuffle buffer needs to be, which in this case is 60,000. And then we're overriding the variable. We're then taking the data set again, and we're batching it into batches of 128 images. Batch into 128 images per sample. So now our data set is now equal to ds.batch, and then we've passed through 128 to there. And then we're prefetching, so this eliminates bottlenecking or slows down, reduces the likelihood of bottlenecking. So again, we're taking our ds variable and we're using prefetch, passing through 64, and then that gives us our data set. So if we run that, no issues. So again, we can type in ds.as numpy iterator. And now what we should get back when we type in .next is a set of images, which is 128 samples in length, which should be 28 by 28, I think by 1. So if we go and do that, type in .shape. So there you go. So 128 images because we've gone and batched it into samples of 128. It's 28 pixels. What is that, wide? So I think wide or high, 28 by 28 by 1, right? So that's going to be the dimension. So I believe it's width, then height, then channels. So it's just a grayscaled image, hence why we've got the 1 at the end there. So that is our data set now built. So we've gone and done a ton of stuff here. So first, what we've gone and done, let me make sure we're zoomed out. So we've gone and brought in NumPy for a little bit of data transformation when we're visualizing. So we're specifically using np.squeeze. We're then setting up the connection to the iterator. We're getting the data out of the pipeline using the .next function. We're then visualizing using matplotlib subplots. We're then scaling it. So this is how you define a pre-processing step whenever you're working with the TensorFlow data pipeline. And then I've gone and built up an entire data pipeline here. So we've gone and reloaded our data set and then done the Mxshabat shuffle. So we've gone and mapped it, we've gone and cached it, shuffled, batched, and prefetched it, which gives us our data set that looks like this: 128 samples by 28 pixels by 28 pixels by 1. Cool. That is step 2 now done. So we've now gone and visualized and built our data set. let's jump back on over to our client.
Time to build the model, my guy. Oh, I was born ready to model, my guy. Oh, wait, what? What are you talking about? Anyway, now what we're going to do is build two models. The generator model will be built to try to generate images of clothing and fashion. The discriminator will try to learn to spot the fakes. So the generator is almost like an artist trying to forge things, and the discriminator is an art critic trying to spot them out. Exactly. Let's do it.
Radio. So we're now up to the good bit, actually starting to build our deep neural network. Now, as I mentioned in the client conversation, so there's a couple of key components that we actually need to build here. So namely the generator, and think about this as the part of the GAN that is actually doing the generating. So we can pass through a bunch of random numbers and it will try to take that set of random numbers to generate some fashion. Now, there is a type of generative adversarial neural network that actually gives you a little bit more control, and this is called a conditional GAN. So you can actually pass through the number 1, which might map to a specific type of image, and it will actually try to generate that image. So we're not going to use a conditional GAN for this tutorial, but if you want a video on that, let me know in the comments below, and maybe we'll try to wrap something up that does that. So the first thing that we actually need to do is actually import our modeling component. So we need to bring in some more dependencies. Namely, we need to bring in the sequential API, and we also need to bring in the layers that we're actually going to use. So let's go on ahead and do that. .keras.layers import. What do we need? Okay, those are our modeling components that we're going to need. So the first thing that we've actually gone and done is brought in the sequential API. I think I went through a detailed explanation of how that works in one of the previous videos. It was either the image or the eye detection, iris tracking video, or the one or the face detection one. But just know the sequential API means that we take in one input and we get to one output. It's basically flowing one way. So that is the API that we're going to be using. So bring in the sequential API for the generator and discriminator. And the cool thing is because the generator is just going to take in a random number of random values, so effectively a latent set of latent values, we can do or use the sequential API for that. Likewise, the discriminator is going to take in an image and try to output a set of binary classification values. So 0 or 1, 1 or 0 to determine whether or not it is a real or fake image. So the generator is going to take in random values, try to generate an image. The discriminator is going to take in the generated image and maybe some real images and try to determine whether or not it's fake or not. And it's sort of like this balancing act between them. That's how we actually go about training these bad boys. So that's the sequential API. Then we're bringing in a bunch of layers. The layers for the neural network. How cool is this that we can actually live in a day and an age where we can build AI stuff? All right, so for our neural network, we've brought in from tensorflow.keras.layers, import conv2d, and then we are also bringing, so convolute, that's going to allow us to perform convolutions. I believe we're going to use that in both the discriminator and the generator. We're then also going to bring in our dense layers, which are fully connected layers, flatten, which allows us to flatten a set of dimensions or vectors or matrices. We are then bringing in the reshape layer, which allows us to transform what the output from a previous layer looks like to a different shape. Pretty useful whenever you're taking in inputs of a certain shape. So we're going to use this to take in our random variables for our generator and reshape it into something which gives us a little bit of spatial quality. You'll see that in a sec. We are then bringing in leaky relu. So that is just an activation. Leaky relu versus relu. So I find it useful to actually visualize what the activation functions look like. So a relu is just this value here. So it'll just be the blue line, and then following the x-axis, the leaky relu has a little bit of a leak on the negative set of values, right? So that allows us a little bit more data to transfer. Then we've got dropouts, a form of regularization, and we've also got upsampling 2D, which is going to be used for our generator to upsample the images and add in a little bit more depth to, or a little bit more space to our image. Okay, so these are all the layers that we're going to need. So we're bringing the sequential API and then a bunch of different types of layers. So that is or those are the modeling components that we're going to need. And the next thing that we want to do is actually build up our generator. So let's actually go and do this. So we are going to create a new function and we'll call it build generator. And then we're going to instantiate our model. So model equals sequential. And then we're going to start adding a bunch of layers, and what we're going to return at the end is the model, right? So what we actually need to do in the interim now is actually work out how to build this generator. So the first thing that we're going to do is define what number of inputs we're actually going to take in. So we might take in, let's say, 128 values and use that as our random sampling value to actually work out what to generate. So that's exactly what we're going to do. So let's build our first block, and then we'll take a look at what that looks like first up. Okay, that is the first block that we're going to add to our deep neural network. So we've gone and added in a dense layer, leaky ReLU layer, and a reshape layer. So let's see if we can just generate this to begin with. So model, let's call it test model for now. Test model equals build generator. And we've got an issue, takes 2 positional arguments, but this should be wrapped again here. One more set of arrays there. Okay, cool. All right, so that is our test model now defined. Can we type in .summary? Beautiful. Okay, so that is what our initial model looks like. And I find building up this way actually makes a little bit more sense because you can actually see what's happening. So the first thing that we're doing is we're specifying what our input layer is going to be. And our input layer is going to be a fully connected layer, or a dense fully connected layer. Now the number of units is going to be 7 by 7 by 128. Now let me explain why we've gone and specified that. We are going to be passing through 128 random values to our generator to help it determine what to generate from there. Now this is why I sort of mentioned that you don't have as much control with this type of GAN as you do with a conditional GAN, because a conditional GAN is going to focus on what type of image you want to generate. With this type of GAN, it's really just generating random images from your sample population. So it'll be trying to generate random fashion images. Now, the nice thing is that we can avoid something called mode collapse, which still ensures that it generates a bunch of random different types of images. So it might generate some jumpers, might generate some shoes, might generate some singlets, so on and so forth. But just know that that input value that we're going to be passing in, which is the 128, is what gives our generator some context to determine what to actually generate. So we are going to generate based on 128 random values, normally referred to as the latent space as well. So that 128 is then going to be converted into a spatial area. So the 128 values, think of it just like an array of 128 values. But because we want to eventually convert this into an image, we want to give it some spatial qualities, right? So we're actually going to convert it into a shape of 7 by 7 by 128. And that is what our dense layer is going to do. So the number of units that we're going to have is going to be 7 by 7 by our random variable. So this could just be our random variable here. So model.add, and then we're passing through dense, and then 7 by 7 by 128. We could just pass through the actual value there. And then we're specifying what our input value is going to look like, which is going to be 128 values. Then we are applying a activation. So we're specifying that we want to apply a leaky ReLU after the fact. This allows us to cater for non-linearities in our model. So model.add, and then we're passing through leaky ReLU and we're specifying what that output parameter is. So 0.2. So that is what defines how far that bottom bit looks like. And then we're reshaping it. And this is what now gives us our spatial quality. So we're passing through model.add, and then we're passing through a reshape layer, which takes our dense output, which is really just going to be 6,272 values. And we're going to effectively be converting it to the beginnings of a image. So, except it's an image which is 7 by 7 by 128 channels. So it's a monster image with a ton of layers. Eventually, we're going to get to the point where we are generating, or this is outputting an image which is the same shape as our data. It'll be 28 by 28 by 1. So we're starting out with 7 by 7 by 128. We're eventually going to get to 28 by 28 by 1 by adding in a bunch of additional layers. So this is our first block. So it takes in random values and reshapes it to 7 by 7 by 128. So, and just think of this as the beginnings of a generated, let's put this on another line. Beginnings of a generated image. Coolio. All right, so that's the first set of blocks now done. Now, this is obviously not our model complete because right now it's still outputting 7 by 7 by 128, which is not in the correct dimensions for a generated image. It needs to be 28 by 28 by 1. So everything that we do from here on out is really to get it towards that shape. So in order to do that, we're going to be using the conv 2D layers, and we're also going to be using the upsampling 2D layers to get us to 28 by 28 by 1. So let's add in a bunch more layers. Okay, that is our first upsampling block. So again, the upsampling block is effectively going to double this spatial quality. So we should be going to 14 by 14 by 128. We're then passing it through a convolutional layer, which should effectively condense it down a little bit, I believe. Oh, well, it's padding same. It might not. Let's actually take a look at that in a second. But so our convolutional neural network layer is going to have 128 units. So it's going to preserve the number of channels. Our kernel size is going to be 5 by 5, and our padding is going to be the same. So it should effectively not crop, but we will see. Actually, it will crop because we're using a bigger filter, but we will see in a second. And then we are passing through our activation, which is going to be a leaky relu again. So let's run this. So now, okay, so it didn't crop. So now our output is now 14 by 14 by 128. If we really wanted to, we could actually just apply the exact same upsampling block. So we could literally just take this again and change the number of filters here. Let me actually show you rather than talking about it, right? So if I grab this, pasted that there, and said, rather than having 128 kernels here, give me 1. Boom, boom, boom. Take a look. That is our output layer now outputting the same shape as an image. So we could actually stop there, but there's not really enough. Typically, you want to add in a bunch more layers for your generator, because this gives it a little bit more sophistication in terms of actually being able to generate something which is sufficiently complex to look like a generated image. So we are not going to do that just yet. We're going to add in a bunch more layers in between there to give us a little bit more information. Okay, so what we've gone and done is we've gone and added an upsampling 2D block, which effectively doubles the size of our output from our previous layer. So it's literally going to go 14. Let's actually show you, or let me show you. So if I actually deactivated those 2 additional layers, boom, boom, boom. So it's literally going to take that layer and it's going to double it by 2. So it's performing upsampling. So, or not doubling, but it's actually expanding the values that it's got. And I believe it's just duplicating it by, it's taking the value next to it and sort of copying it over. But then we pass it through a convolutional 2D neural network to then condense that information and provide a little bit of parametric values or parametric transformations to it. Because you can see that there are no parameters for our upsampling layer. Right, so let's add our convolutional layer. So boom, 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 boom. Now we've actually got some parameters that our neural network can learn to be able to generate a better set of values for our output. And then we're passing through a leaky relu layer. So this gives us our activations. Boom, so that's our leaky relu. So we're now gone up to 1 million or 1.2 million different parameters for our deep neural network. And we're getting closer to what our output image needs to be, which is 28 by 28 by 1. Okay, let's add in another upsampling block and we'll go from there. We'll see where we're up to. Okay, so I've gone and added 3 more blocks there. So let's just say that's downsampling block 1, even though it really isn't downsampling. So I've literally gone and copied this upsampling block down here. So it's again, just copying the exact same layers, which will give us the output of 28 by 28 by, 128. We're then applying another set of convolutions and a leaky relu. And again, we're applying the same padding. So it really shouldn't just change the size of our output. Again, we're going and doing the exact same. So this is really just giving us more knowledge or the ability to have more parameters in our deep neural network to learn a little bit better. So really, it should be 28 by 28 by 128 in terms of our output. So if we go and run these, boom, 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 right? So we're now at 28 by 28 by 128, which means that all we really need to do is add a final convolutional neural network layer, conv layer, to get to one channel. So let's add that final layer, and that should be our neural network, or at least our generator built. Cool. So that's our final layer. So this is going to, remember, we want it to be one channel. So previously we would have had 128 channels based on all the kernels that we had in our convolutional neural network layers. Because we now have one filter, we're only going to get one channel out in our image, or our generated image. But remember, we preserved the shape. So we had 28 by 28. And this was really just by passing it through two different upsampling layers. We went from 7 to 14, 14 to 28, which now gives us, so if we go and run this once more, we are now at 28 by 28 by 1 with a model which has 2.15 or 2.16 million parameters. So we're now looking good. So that is our generator now built. So we've gone and instantiated the sequential API. We then went and did a little bit of reshaping from our input dimensions of 128 random pixels, went to 7 by 7 by 128, passed it through an unsampling block, which went to 14 by 14 by 128, passed it through another upsampling block, which took it to 28 by 28 by 128, and then we went and passed it through some additional, it's not really downsampling, let's just call this a convolutional block. I don't like telling you it's a downsampling block, and it really isn't. Because downsampling would mean we reduce that spatial quality, possibly bump out the number of channels. We're not doing that. Right, so then we're taking it through two upsampling blocks, passing it through two convolutional blocks, and we're maintaining the spatial shape because we're setting padding equal to same. So two of those, which means that we're really just going to have the exact same values. So it's not exact same values, but the exact same output shape. It'd be 28 by 28 by 128. And then we are passing it through to our final layer, which is going to reduce the number of channels. So model.add, we're passing through a convolutional 2D neural network, specifying that we only want one filter or one kernel. The kernel size is going to be 4 by 4. We're specifying padding equals the same because that means we're going to preserve that 28 by 28. And we've got an activation of sigmoid because we actually want our values to be between 0 and 1. This is what's going to allow us to generate an image. So if we go and run through this now, take a look, our neural network is 28 by 28 by 1. So that is our generator now built. Now we can actually go and test out our generator. So let's minimize this a little bit. So we can actually go and pass through some random values to our generator, and we should be able to output some stuff. So let's try it out. Awesome. So that is our generator now generating values and effectively images. So I went and renamed the model to be equal to generator. So that's going to be the name of our model over here. So generator equals build underscore generator. We can take a look at our summary as we did before. And then to generate an image, we can pass through generator.predict. So use the predict function and then pass through those random values. So here we're actually generating 4 different random images. So I've used NumPy. So numpy.random.randn. So this generates a set of numbers using a normal distribution. So we're passing through how many images we want to generate. So 4. And then we're passing through those 128 random values, which is what our model expects to be able to generate some images. And then I've just printed out the array, which is over there. Now, rather than visualize or just looking at the numbers, we can use matplotlib again to actually view what our random images look like at the moment. So we can actually take the visualization script that we had from over here. So we can copy that and we can actually just tweak it a little bit to be able to plot this out. So we can take, so this bit is going to be the same. We're actually looping through each of our images. So let's say for idx comma image in enumerate image, and then let's just double check what our image shape looks like. So we are 28 by 28 by 1. Okay, so that should work. So this will grab one image, one index. We can get rid of the sampling from our data iterator. We are just going to be passing through our image here. Image. Index should be preserved. That's fine. We can pass through our index here. Let's see if that works. There we go. So those are the images that we've just gone and generated. So all I've done is I've taken the exact same visualization script that we wrote right up here. and I've gone and adjusted it so that we can now visualize the images that we're outputting from our generator model, really. So what we're doing is we're looping through each one of our images. So for index, comma, image in enumerate our images. So this is going to give us an index and the actual value from that specific array. We're then using the specific axes from our plot.subplots function, and we're using numpy squeeze to squeeze down our values, because remember it's 28 by 28 by 1. By using numpy squeeze, we're going to get it by 28 by 28. So it just makes it a little bit easier to visualize. And then we are plotting out each one of those images. So we can see 0, 1, 2, 3. So that's what they look like at the moment. Pretty crap. But once we actually train these, this will actually be able to generate a better set of visualizations and better set of fashion components. So if we go and run this again, we can get rid of this image because that's causing a nightmare. We can delete the shape. Boom. So that's our next set of images. So bang, bang. That's our next set. Next set, right? So I can actually grab this, put it into here. You can say generate new fashion. So right now it's looking pretty crap, but that's because we haven't changed it, right? So new images, new images, new images. And you can see it's generating different types of stuff because we are random sampling or producing a random sample to pass through to our initial neural network. So pretty cool, at least to begin with. So we are definitely going to make this a whole heap better. Let's enable scrolling for that. This is obviously going to get a whole heap better eventually, once we've actually gone and trained it. But that is our generator now done, which is one of the hardest parts of actually building a GAN model. So we've gone and done a ton of stuff. So first up, we've gone and imported our different modeling components. We've gone and built our generator. Remember, we started off with a unique layer, which takes in some random values and reshapes it to give it some spatial qualities. Remember, our reshape layer did that. We then went and used upsampling to expand the size of our image. So we actually doubled the size. Went and applied some convolutional neural network layers to give it a bit of, give it some trainable parameters. And this allows us to give a little bit more information to what that output actually looks like, along with a leaky ReLU. So what we've then gone and done is pretty much use those same building blocks. So here, to be able to increase the size from 7 by 7 by 128 to 28 by 28 by 128. We've then gone and added a couple of additional convolutional neural network layer blocks. And then last but not least, this last layer, really, really important, reduces it to one channel, which is the same size as our input data. We've then also specified an activation of sigmoid to give us a value between 0 and 1. Okay, that is our neural network looking pretty good. The next thing that we need to do is build our discriminator. Funnily enough, this is probably the easier part of building and working with GANs, because the discriminator is really just a image classifier that is determining whether or not the image is real or fake. So if you've watched my image classification tutorial, it's really no different to that. We're just adding in a bunch of dropout layers to increase the regularization, because image classification is a pretty easy task for neural networks. Generating new stuff is a little bit trickier. So we want to make it a little bit harder for a discriminator to learn. So what we're going to do is create a function, def build discriminator. And we are going to effectively do a similar thing to what we did for our generator. So we're going to instantiate our model using the sequential API. And eventually we're going to return our model. And then just to make it a little bit easier to see what we're actually building, let's set up a similar thing to what we did for our generator. So we're going to create an instance of our discriminator. So discriminator equals build discriminator. And eventually, once we've gone and constructed it, we'd actually be able to type in discriminator.summary, right? But right now, these two lines aren't going to work, because if I go and run that, first up, it's not defined. Oh, it actually will work. So this line won't work because we haven't actually gone and passed through any layers to that. Okay, so the first thing that we actually want to go on ahead and do is build up our discriminator. So let's go and do it. Okay, that is the first convolutional neural network layer block. So let's take a look. So we've gone and written 3 additional lines there. So we've added a convolutional neural network layer, a leaky ReLU activation, and a dropout layer. So the convolutional neural network layer is going to have 32 filters. So model.add conv2d, passing through 32 filters. The filters are going to have the shape of 5 by 5. We're not specifying padding equals the same. So this means it's going to start condensing down the information that it's getting. specifying our input shape as the same as the output shape of our generator. So our generator is going to generate an image of 28 by 28 by 1. We then pass that to our discriminator to determine whether or not it's a real or fake image, with the end goal for our generator to generate images which our discriminator thinks are real. So it's a bit of a trade-off, which we'll sort of tweak in our training loop to get to work. So the input shape is going to be the size of the output shape of our generator. So 28 by 28 by 1. Adding through a activation layer, which is going to be a leaky ReLU. Leaky ReLU is actually recommended practice when building GANs, or at least in a lot of them that I've seen, they're using leaky ReLUs as activations rather than just a straight ReLU or sigmoid or tanh. Okay, so model.add leaky ReLU, specifying 0.2 as the input parameter, and then we're passing through dropout because we want to make it a little bit harder for our discriminator to learn. So dropout effectively applies some regularization. So model.add dropout, and we've specified the positional argument for that as 0.4. So that's the strength of the dropout. So that's our first convolutional block. And if we take a look, once we run through those two new lines, so to build the discriminator, we can use the build discriminator function, and then discriminator.summary allows us to see what it looks like. So right now our shape is 24 by 24 by 32. And that is what we're outputting, and we've got 832 params. So a very small model at the moment, but we're going to build on this. So let's add in a bunch of additional convolutional neural network layer blocks and then get this down to what is effectively an image classifier. Okay, so I'm adding a second convolutional neural network layer block, and it is pretty much identical to the first one. The only difference is I've dropped the input shape because we don't need to define the input shape anymore because it's not the first layer or first hidden layer. And I've bumped up the number of filters to 64. I'm probably going to copy this again and create another one with 128. And then let's take a look at what that shape looks like. This is going to be our third conv block. So we're now down to 16 by 16 by 128. So we're getting closer to just having a single output value, which is a sigmoid, which has, what would it be? It'd be sigmoid, so 0 to 1. Okay, so we're getting there. So let's go, and I'm going to add in a bunch more layers. But basically, it's going to follow this similar pattern. We're then going to flatten it down and then output a single value using a dense layer. So let's do it. Okay, so that is my fourth convolutional block. I don't think I'm going to add in another one. I think we're good for that. I'm just trying to mimic the exact same model that I pre-trained earlier so you guys can use the trained weights that I've got. So we've effectively got 4 different convolution blocks. So the first one with 32 filters, second one 64, third one with 128, last one with 256. Now what we're going to do is we're going to flatten this model. Actually, let's take a look at our output first. So if I go and run this, we have an output of 12 by 12 by 256. So by flattening it, we'll actually get 12 by 12 by 256 being passed to a dense layer. So let's do that. So flatten, then pass to dense layer. So model.add, and then we're going to pass through a flatten layer, which should flatten it down. We are then going to pass through a dropout layer. So model.add dropout 0.4. I wonder if it's best practice to add a dropout after a flatten. Anyway, I've added it in the pre-trained model, so we kind of need it now. So add, might take a look at that. Let me know if you get better performance by removing that layer, but for now, we're going to leave it. So we are now going to output a single value, and our activation is going to be a sigmoid because we want the output value to be between 0 or 1. So 1, I can't remember the way I configured it, whether or not 1 is representing a false. Let me just double check. So yeah, so 1 represents a false image, or 1 is eventually going to represent a false image. 0 is going to represent a true image. So again, you can play around with that anyway. Activation equals sigmoid. And that looks good. I think that's our model done. Yeah, cool. All right, so you can see that we're originally taking a image which is of the shape 28 by 28 by 1, and then we're finally going all the way down to the bottom, and we're outputting a 1, which will be a value between 0 and 1 to represent true or false, whether or not the image is fake or real. 1 being a fake image, 0 being a real image. So, and again, different implementations run this different ways. 1 might be a real image, 1 might be a fake image. It very much depends on how the model was actually set up. Now, we could actually take those images that we actually generated from our generator, right? this is what's cool about it. You can prototype some of this. You can take this image over here and pass it through to our discriminator, and it should output a 0 or 1. So if I went discriminator, let me bring this up, discriminator, I can never type this, predict and pass through image. We've got issues. All right, so negative dimension size caused by subtracting 1. What have we gone and done there? Do we need to pass through .predict? No, we've got an issue. All right, let me debug this. Wait, we've got one image inside of image.shape. So the model is okay. Wait, I thought we had batched this. So for image.shape. Okay, that should work. So I'm guessing that we're getting an error because we're passing through a single. So it should be 4 images now. Okay, there we go. That works much better. So .predict. Okay, makes more sense. So the reason that we're getting that error is because we were trying to run a single image through to a neural network, which is going to throw an error. So it's effectively like doing that. So you can see that that's our image. If we take a look at the shape, it's 28 by 28 by 1. If I run that, typically when you're passing through an image or a single image to a deep neural network, it expects the batch number to be first. So because this is a single value, it's a single image in a batch. So we'd actually need to type in np.expand dims, pass through the parameter 0, fixed. So now we can generate a prediction on a single image, which you can see is 0.5. So it's not very confident whether or not this is real or not. But again, we're going to train a better generator once we get through that. Now, if you've got more than one image, you don't need to go and wrap it in expand dims. You can actually just go and do this. So if I go and generate a new set of images from up there and then run it through our model, run it through the .predict function, should get no errors. Boom. Take a look at that. Pretty cool, right? So that is our generator and our discriminator now built. And you sort of saw how I'm building up these layers to ensure that our input and our output are of the correct shape. So remember, our generator is going to take a set of random values, which in our case are going to be 128 random values, and it's going to output an image or a vector or a matrix of the shape 28 by 28 by 1. Now, our discriminator is going to sort of do the opposite of that. It's going to take the output of the generator, so 28 by 28 by 1, and it's going to output a single value between 0 and 1 to determine whether or not it's real or fake. Cool. Okay, that is our set of generators now done. Let's go jump back on over to generators and discriminators now done. Let's go and have a chat to our client.
So that's done. What about the custom training loop? That's one of the most important parts when building GANs. We'll write a custom training loop to train both the generator and the discriminator simultaneously. Got it. Let's go.
So we're on the home run now, but this bit is pretty hardcore. I want to disclose that, but we're going to take it step by step. So the training of GANs is notoriously difficult, and nobody actually really tells you why it's difficult, but I'm going to give you my feedback. So the reason why it's difficult is you need to find a balance between the speed at which the discriminator trains and the speed at which the generator is able to learn. So a big thing that we need to do whenever we're training these side by side is ensure that our discriminator doesn't train too fast so that it's able to smash out and know what a fake image is every single time. So balancing that is really, really difficult and is really, really important to ensure that you get that right. One way that we help do that is we actually inject some random noise into the outputs from the discriminator, almost to kind of like trick it and slow it down a little bit. Now, the other thing is that it takes quite a fair bit of time to train one of these that is actually generating good output. So if anybody goes, hey, you can train one of these in like 10 minutes, then be very, very skeptical. That's just my feedback. And again, you might get different output from some experts out there in the field, but that's just my experience. So just keep those two things in mind. But we're going to take this step by step and go through it. So constructing a training loop. Now, what I mean by a training loop is, so typically when you go and train a deep neural network using TensorFlow or PyTorch, you can typically, there's a couple of key steps, right? So you instantiate the model, so maybe create model equals sequential, and then model.add a bunch of layers, then model.compile, which actually assigns a loss function and an optimizer, and then model.fit, which is actually what goes and trains the model. Now, because because GANs have two components, so a generator and a discriminator, you actually need to train them side by side, which means we can't just use .fit. We need to do something a little bit more tricky to ensure that we get this to work. So what we're going to do is define our own custom training loop. And by training loop, we're just changing what the .fit function does by defining our own training step. So we're going to do that over here, and we're going to do it using a subclass model. You can also do it using @tf function decorator. There's some good documentation on the TensorFlow website on that. I'll link to it below. But for now, we're going to do it this way. And as per usual, all this code is going to be available via GitHub. So don't stress. If you don't get it, you can go back through and take it at your own pace. Okay. First thing we need to do is set up some losses and optimizers. So in order to do that, we actually need to bring in some losses and optimizers. So let's do that. We're going to use the, what is it? Binary cross entropy for, I think we're actually going to use binary cross entropy for both. Because, yeah, now we'll come back to that. We're going to use binary cross entropy and we're going to use the atom optimizer. So first thing, let's import those. So I'm going to import some optimizers from Keras. So from tensorflow.keras.optimizers, we are going to import atom, and then from tensorflow.keras.losses, we are going to import binary cross entropy. Cool. So our atom optimizers is going to be the optimizer for both, and binary cross entropy is going to be the loss for both. Now you're probably thinking, Nick, what the hell? How are you going to use binary cross entropy when your generator is outputting an image? Well, what we actually do with that image is we pass it through to our discriminator, and we determine whether or not our generator has actually produced an image which is able to trick the discriminator. So we actually reward it for getting our discriminator to produce the wrong value, which is kind of not intuitive, but once you actually play with these a bunch of times, you'll actually be like, oh, that's actually kind of cool. So we're actually rewarding our generator for tricking our discriminator, and we're rewarding our discriminator for getting it the right one, or determining what type of image it actually is. Cool. All right. So those are our losses and our optimizers. So from tensorflow.keras.optimizers import atom. You can try stochastic gradient descent or another type of optimizer. Atom is probably what I use most of the time. And then for our losses, so from tensorflow.keras.losses import binary cross entropy. Pretty cool, right? Like, so if you actually go and build some other, I know I'm veering off into the wayside, but when I was actually building the super resolution model, I actually had to use a combination of different types of loss functions. So I actually use mean squared error for the perceptual loss, and that is how different the actual values are from a real super resolution image versus a not a super resolution image. And what else did we use? Perceptual loss. I think I didn't use binary cross entropy, but I used a combination of a bunch of different types of losses. So we actually took the discriminator loss versus plus the perceptual loss as the final loss function. But again, I'll probably go through that once we actually go through that model. Okay. So that is we've imported our optimizers and our losses. Now we need to create instances of them. So we're just going to create sample or examples. So we'll go gopt equals atom, and we're going to set the learning rate equals 0.0001. So our learning rate for our generator is going to be faster than the learning rate for our discriminator, because we don't want our discriminator to go too fast and absolutely smash our generator. And this is part of the learning process, right? So you might need to tweak this if you're doing different use cases, but I found that this has worked. All right, so we're defining our two optimizers. So I've typed in gopt equals atom, and I've specified a learning rate of 0.0001. And then for our discriminator, I've created an optimizer. So dopt equals atom, and then our learning rate is 0.0, so there's just one extra zero, so 0.0001. Cool. And then I'm going to define my losses. So gloss equals binary cross entropy, and then dloss also equals binary cross entropy. Boom. Okay, those are our losses, and our optimizers now set. So again, the reason that we're specifying the learning rate for the discriminator slower is just so it doesn't blow out and learn way too fast and cause our generator to lose the plot. And we've also gone and defined our losses. So that is step 4.1 now done. So set up our losses and optimizers. Now is the big boy. So setting up the subclass model. So first thing that we need to do is import the model class from Keras. So from TensorFlow, gosh, I can't type, TensorFlow.keras.models, import model, and this is the base model class. So once you get to this level, you've got a ton of control over what TensorFlow does. So you can do a ton of stuff if you want to. So this is importing the base model class to subclass, our training step. Cool. All right, so I've written from TensorFlow.keras.models, import model. Now, when you're defining new models, there's basically like two key functions. So we're going to create a GAN, so class, fashion GAN. You can name it whatever you want. And we are going to pass through our base class. And then there's a couple of key methods. So again, method is inside of class. So there's a couple of key methods that you need to define when you're subclassing a model. So def init, because we need an initialization function. We'll come back to that. Def train step. And this is what actually does our training. You can also define, and so keep in mind, train step is called when you call the .fit function, right? So this is really, really important to note. If you wanted to run an evaluation function, you'd also create a def test step method. We're not going to use that, but just a key thing to note. We also need to have a compile method. So def compile. And again, we'll come back to that. So those are the key methods that we actually need to define in our subclass model. So, and the reason that we're going to define a subclass model is because we're going to do some fancy crap inside of this test step model or test step method. The other way that you'll see people do it is they'll actually write at tf function, and then they'll actually write a custom test step or custom train step. They'll do it sort of like that, and then they'll do a whole bunch of other stuff. But for now, I just like a little bit more control with the subclass model, but just keep in mind that you've got a few different ways to actually go about doing this. Okay, so first thing that we need to do is go and pass through some parameters to our init method. So let's actually go on ahead and do this. Alrighty, those are our parameters that we're going to be passing through to our init method. So we're passing through our generator, passing through our discriminator, we're passing through any positional arguments and any keyword arguments. So this gives us a little bit of flexibility if we want to go and inherit from our base model. Then we're going to run super.init, and we're going to pass through any of those arguments. So again, if we want to go and use some of the base functionality inside of our Keras model, we've got the ability to do that now. So we've passed through those arguments and keyword arguments to our base model, to our base class effectively. Then the next thing that we're going to go ahead and do is set up two attributes for our generator and our discriminator. So that means that we're going to be able to refer to them inside of the model. So let's actually, so create attributes for gen and discriminator. Self dot, we'll call it generator equals generator. Self discriminator equals discriminator. We can get rid of the pass. I think that's it for our init method. Yeah, that's pretty much it. So we've gone and written, what have we gone and done? So we've gone and passed through our generator and discriminator model. So we'll instantiate those before we actually go and, or we'll instantiate those, then pass them to our subclass model. And then we're passing through any keyword arguments and any positional arguments to our base class. So this pass through args and kw args to base class. And then we're creating attributes for our generator and discriminator. So that is our init method now done. Now, the next thing that we need to do is actually go and compile. So to this, we're going to need to pass through our optimizers and our losses, and we're going to need to run super.compile. So let's do that. Cool. All right. So that is those are the input arguments that we're going to be passing through to our compile method. So we've got def compile, and then we're passing through our generator optimizer, a discriminator optimizer, a generator loss, and our discriminator loss. We're also going to be passing through any arguments and keyword arguments we might need, because we're going to call. So compile with base class. So we're going to run super.compile, and we are going to pass through our arguments and our keyword arguments. Boom. Okay. And then we're going to create attributes for each one of these. So attribute for our optimizers and attributes for our losses. So let's go and do that. Okay, that is our compile method now done. So let's quickly recap. So we've gone and defined our init method, and our init method takes in two key things, right? Takes in our generator and our discriminator models that have already been instantiated. You can ignore the super bits for now, just know that they're necessary evils, right? So we're going to be passing through any additional arguments that we want to pass through when we create this model via that. So then we're creating attributes for our generator and our discriminator. So we're going to be able to refer to them as self.generator, self.discriminator. Likewise, we're doing something similar for our compile method. So we're passing through our optimizers. So gopt, dopt, gloss, dloss. And remember, we've already created those over here, right? So we're effectively passing through atom, binary cross entropy, binary cross entropy. And then we're creating attributes for those inside of our fashion GAN class. And again, this could be you could name it whatever you wanted to. It's just the naming convention that I've gone and taken for the fashion GAN. Okay, so those are the two easier bits now done. So we've gone and done the init method and the compile method. I know it's always a little bit painful. So all right, now we're going to get onto the big boy. So for our train step, the first thing that we need to take in is our batch. And this is a batch of data. Keep in mind, a batch of data in our case is going to be 128 images of the size 28 by 28 by 1. And that has been defined right up over here. So when we went and created our data set up there in step or section 2. Now what we need to do is actually do something with that data. And that is exactly what we're going to do inside of our train step. So the first thing that we're going to do is we're going to get a batch of data. So we'll call it real images equals batch. So this first step is get the data. Right, so we're getting, first things first, we're getting a batch of real images, and then we're going to get a batch of fake images or generated images, right? And this is going to be self.generator, tf.random.rand, we'll just call it .normal. And this is effectively what we did previously, right? So we went and created some random images. Remember we used mp.rand.randn? Let me show you. Where did we do it? It was... No, that's the data iterator. We did it over here. So we called mp.random.randn. Pretty much the equivalent of that with using the TensorFlow library is tf.rand.normal. tf.rand, is it random? Yeah, random.normal. And we'd be passing through, I don't know, like 6, 28 by 28 by 1. I'm going to do it. Probably needs to be wrapped. There you go. So what we're doing is we're effectively generating those random input values that are going to be going into our generator, right? So again, these, actually, wait, it's not 120. It should be 6 by 128 by 1. Those are our random values. So we're passing through random values and we're sending those through to our generator model to be able to generate random values or generate random images to begin with. And this is because we need real images and we need fake images in order to go on ahead and train our model. So let's go and do that. So we are going to generate, let's generate 128. So we've got the same number of images in our real images as our batch. So 128 by 128 by 1. And we can close that. And then we're going to specify training equals false because our deep generator is not training at the moment. We're just making predictions. Okay, so that is that. Now, the first thing that we're going to do is train our discriminator. So train the discriminator. So there's 3 key steps that we need to do in order to go and train our discriminator. So the first one is we are going to pass the real and fake images to the discriminator model. We then need to create labels for real and fake images. We are then going to pass through or add some noise to the outputs. And this is what helps it from learning way too fast. We then calculate the loss and then apply propagation. And this is what effectively allows our neural network to learn, right? And I'm just going to tab these in. Okay. Now, in order to actually go and train our discriminator, we need to start calculating our gradient. So we can do this using the tf.gradient tape method. So let's go on ahead and do this. So that is setting up our gradient. So this is going to start calculating or monitoring each one of our functions. The next thing that we want to do is actually this next step. So pass the real and fake images to our discriminator model. So let's do that. Okay, so those are the initial predictions, right? So we've gone and written 3 lines of code there. So let's break that down. So the first line is actually taking our real images and we're just passing that through to our discriminator. And we're storing the values inside of a variable called y_real. So y_real equals self.discriminator. We're taking these images from over here and we're passing it to the discriminator model. That's all we're really doing. We're passing through training equals true because this means that the dropout is going to activate, right? So if you pass through training equals false, dropout layers aren't going to run. Then we're also doing the same for our fake images. So y_fake equals self.discriminator. We're passing through our fake images from over here. And again, we're specifying training equals true. And then we're combining it into one set of outputs. So y_real fake equals tf.concat. So this just concatenates them both together. And we're going to be passing through our y_real and y_fake, so that, and we're combining on the 0 axis. So it's going to combine all the samples together. Cool. So that is the first step now done. So we've actually gone and produced predictions as to whether or not our discriminator thinks the images are real or fake. The next thing that we need to do is actually create labels, because remember, this is effectively a supervised learning problem at the moment. We're determining whether or not they're real or fake, 0 or 1. So let's go and do this. Okay, so those are now our predictions. So we've actually gone and assigned the labels. And really, you could go and well, actually, you can't really pre-generate this because we're generating new predictions each and every time, but that's fine. So we've now gone and created a new variable equal y_real fake. So this is the equivalent of this over here, right? But these are the predictions from our discriminator. These are the actual labels. So y_real fake, and I'm just setting the order so you know what order they're in. So in this particular case, again, we're creating a set of labels for our real images. So, and the real images are going to be 0. So really our discriminator is all about spotting fakes. And we've set that equal to tf.zeros_like, and we pass through y_real. The cool thing about this is it effectively goes and generates a set of zeros based on the shape of your input. So in this particular case, we're passing through our image or our y_real values, and we're saying all of these should actually be 0. So it's going to be in the same shape as our real or our predictions, but they're going to be 0s. Now we're going to do the same thing for our fake. So tf.ones_like, we're passing through fake. So effectively, we're going to have 128 zeros and 128 ones over here. And those are going to be the labels for or the real labels for our predictions from our discriminator. So think of this as your true y values. And we're going to concatenate both of those together using tf.concat. So our final value is going to be y_real fake. Okay, so we've now gone and made our predictions. We've now gone and created our labels. And let me just quickly show you what zeros_like actually does. So if I actually go and wrap this set of, actually, let's not do it with that's our latent variables. So let's just enable that. So what would it be? It would be, it'd just be like something like that, right? So it'd be predictions like that. So if you can see that we've got a bunch of random values, right? So if I type in tf.ones_like and pass that, you can see it's generating a bunch of ones, but in this same shape over here. Now, if I did tf_zeros_like, it's generating a bunch of zeros. Now, if I go and concatenate those, so tf.concat, that, and if I put this inside of an array, and let's say ones_like, and let's close that array and then type in .axis equals 0. So you can see we've just got a massive array and we've got a bunch of zeros and a bunch of ones. So that is effectively what we've gone and done in this line. Now what we need to do is add some noise to these outputs, and then we can calculate loss and apply backprop. And that's the discriminator training component now done. Cool. So that's our noise added to our y true value. So in this particular case, we've gone and added a random value between, and we've multiplied it by a weighting of 0.15 for our real images and negative 0.15 to our fake images. So I played around with this a bunch when I was actually testing this out. And I found that adding values to our 0 values and reducing values from our 1 values seemed to work a little bit better. Otherwise, it threw our loss metrics out. So you typically see people just add in a random value to both, not necessarily adjust based whether or not it's a 0 value or a 1 value, so true or false. So in this particular case, I've gone and customized this a little bit, but let's go through these lines. So there's 3 lines here. So noise underscore real equals 0.15 multiplied by tf.random.uniform. So it's a uniform distribution. And we are adding creating the values in the shape of y hat real. So we're going to match that. And then we're adding noise for our fake values. So noise underscore fake equals minus 0.15 multiplied by tf.random.uniform. And then we're passing through the same shape as our as our y hat fake values from over here. Then we're adding it to this value. So we're adding it to our y true values. So y underscore real fake plus equals tf.concat. So we're effectively just concatenating both of these values back. So plus equals tf.concat, and then passing through noise real, noise fake. So that is injecting those noise into the true outputs. Cool. All right, so that is that now done. Now, all that's left to do is actually calculate our loss and apply a backprop. So let's calculate our loss. So total d underscore loss equals self.d loss, which is going to be binary cross entropy, remember? Binary cross. And then we want to be passing through our real, it's y real fake. Actually, not y hat, y underscore real fake. And then y hat real fake. Cool. Alrighty, that is our loss now calculated. So y real fake, y hat real fake, and we are going to calculate that. Then what we want to do is we want to apply backprop. So we're going to go outside of our tf.gradient tape loop, and we're going to first up calculate our gradients, and then we're going to apply our gradients using our optimizer. So let's do this, and then that's our discriminator trained. Cool. That is the training step for our discriminator now done. So I know we wrote a ton of stuff there, but again, this is pretty hardcore in terms of deep learning. So the first thing that we did is we went and calculated our gradients. So we specified a new variable called dgrad, and we set that equal to d underscore tape dot gradient. So remember, using the tf.gradient tape function allows us to calculate all of the operations that are happening by using our deep neural network. And that means that we can use that to calculate our gradient with respect to our loss. So d underscore tape dot gradient, and then the first parameter that we pass through is our loss. So remember, this is our binary cross entropy. And then we want to calculate the gradient for each one of our trainable variables. So we're going to extract our trainable variables using self.discriminator.trainable underscore variables. And then what we're going to do is we're going to apply our gradients using our optimizer. So self.dopt, because remember, we passed through our optimizer over here, which was an atom optimizer. And then we can use .apply gradients to actually go and apply backprop. And so to that, we pass through zip because we want to do our gradient with respect to each one of those trainable variables. So zip, and then we're passing through dgrad, and then again, all of our trainable variables. So it's effectively going to look at the gradient for each one of those variables and apply backprop using our learning rate. Okay, that is our discriminator now done. So I know that that's the hardest bit. Just keep that in mind. That is the hardest bit of the training step. So First thing that we went and did is, again, we went and passed our real and fake images to our discriminator model, and we went and concatenated them together. Pretty self-explanatory, not too crazy there. We then went and created labels for our real and fake images. And remember, our real images are going to have a 0 label, and our fake images are going to have a 1 label. You can tune this. You can do it slightly differently if you wanted to, switch them around. Just keep in mind, you got to change the noise as well and change, I think you can switch them around. You'll be okay. You don't need to go and do anything else. But just keep in mind for now, that's how we've gone and set it up, because it's important because of how we're actually going to go and set up our generator. Then we inject a bunch of noise. So the noise is really just being applied to our true outputs, and this gives us our discriminator a little bit less certainty about whether or not it's predicting correctly or not. So it confuses it a little bit. So we then go and pass just a random set of values. So we're using tf.random.uniform, and we're scaling that by 0.15 for our real outputs, because that adds some values to our zero labels. And then we're subtracting 0.15 multiplied by tf.random.uniform to our fake labels. We then calculate our loss using self.d_loss, which is binary cross entropy. We then go and apply backprop using the gradient tape from up here and the apply gradients method from our Atom optimizer. Okay, that was pretty brutal, but again, it's quite difficult, and that's the hardest bit done. Trust me, that is the hardest bit about actually going and setting up a custom training loop for GANs, and it's probably the hardest one that you'd find in a lot of deep neural networks that you'd actually have to go and build. So congratulations, you just went and wrote that, and you're doing well. All right, now all that we've got to do now is actually go and set up a training step, or the training component for our generator now. So it's going to be similar, but it's by no means as complicated as what we just wrote. So let's go and do our generator now. So again, we're going to use our gradient tape. So with tf.gradient tape as gtape. Now let's actually write, so let's actually call it, so train the generator. Okay, so the first thing that we need to do is generate some new images. Then what we're going to do is we're going to apply or create the predicted labels. And this is a little bit counterintuitive, but I'll explain it. And then we're going to calculate loss. And then over here, we're going to apply backprop. Cool. Alrighty, so let's go on ahead and do it. So that is our new set of images now generated. So I've just gone and created a new variable called gen_images, and I've set that equal to self.generator. And again, it's pretty much the same as what we're doing up here, but this time we're setting our training parameter equal to true. So self.generator, and then we're passing through tf.random.normal. We're passing through 128 by 128 by 1. So this will have 128 random variables which are passed to our generator. And then we're specifying training equals true. Now we're going to create our predicted labels. Now this is a little bit counterintuitive. So over here, when we actually went and created our discriminator, what we actually said was that fake values had the label of 1. Now, because we're trying to trick our discriminator, what we're actually going to do is we're going to set the variables for our generator here to 0. So what we want our discriminator to actually lose out on is we want it to think that our generated images are actually real images. So that's how we're going to calculate our loss for our generator. So you'll see that in a second. So let's actually go and do this. Okay, those are the next 2 lines of code written. So I've gone and written 2 lines of code there. So the first thing is we're running our generated images through our discriminator. So predicted_labels equals self.discriminator, and we're passing through our generated images from here. And we're setting training equals false now, because we don't want our discriminator to be learning whilst we're actually training our generator. So that's just a nuance of how you actually go and set this up. So that is going to generate the predicted outputs, whether or not our discriminator is determining whether or not our generated images are real or false. And remember, a discriminator will output a 1 if it thinks the image is false or not. So over here, you'd expect all of these to be ones. But this is where we try to confuse our discriminator, because what we're actually saying is that our generator loss is rewarded every time it thinks that our discriminator is, or every time it thinks that our generated images are actually real. So when we go and calculate our loss, total underscore G underscore loss is equal to self.gloss. And we're actually saying that the real labels are actually zeros. So we're actually saying that the real images or our generated images are actually fake images. And this is something that took me a little while to get my head around, but this is actually how you go and train the generator. So tf.zeros like, and then we're passing through our predicted labels, and then we're passing through what our discriminator actually predicted. So whether or not it actually predicted true or false. And then from here, what we'll go and do is backprop, and then we'll train our generator so that it's able to produce better images every single time. And this is the trick, right? Trick to training, to fake out the discriminator. Because over time, what our generator will learn to do is produce images which are better at faking outputs through our discriminator. So it will actually start getting zeros by passing it through our discriminator, because our discriminator won't know the difference between a real image and a generated image. So all that's really left to do is actually go and calculate our gradients, apply backprop, and then return our loss metrics. And then we should be able to train. So let's go and wrap this up. Alrighty, cool. So we're now going and applying backprop. This is almost identical to what we did for our discriminator. First up, we calculate our gradient. So ggrad equals g underscore tape dot gradient. We pass through our loss as the first metric. We pass through the variables that we want to calculate the gradient for. So self.generator.trainable variables. Am I spelling that right? V-A trainable V-A-R-I. It should be that. This is spelled wrong. Did I spell it wrong over here? V-A-R-I-A. No, that's good. All right, so then we're passing through what we want to calculate our gradients for, and then we're going and applying our gradients using our optimizer. So self.gopt.apply gradients. We're zipping them because we want to do them both at the same time. So zip, ggrad, and then the trainable variables. So self.generator.trainable variables. All we then need to do is return, and we haven't gone and tested this out. We've gone and written a lot of code and not tested. All we need to do is then return our loss metrics. So d underscore loss is equal to d, should be total d loss. Yeah. So total. And this is important when actually monitoring the model, because you want to ensure that the loss metrics are reducing steadily together in terms of they're not, one is not blowing out versus the other. They're sort of reducing, or they're actually staying stable. You don't really expect them to reduce all that much, to be honest. So G loss is total G loss. Perfect. I think that is done. Who knows? We're probably going to need to do a bunch of debugging for that. But again, all this code is going to be available because we wrote a ton. That is our full subclass model. So fashion GAN, all of that. Quite a ton. Don't ask how long it took me to learn this stuff, but I'm trying to teach it onto you. All right, cool. Let's, we've got our first error. So in line 178, so predicted labels. So over here, we've got an error, and I'm guessing it's because I haven't closed this. It is. And we've got another error. So total G loss. What's happened there? So we can get rid of that. So it looks like we just got misplaced. All right, cool. There we go. So we've now gone and created our subclass model. So it doesn't look like we had any other syntax errors, but training errors is a completely different beast. So let's actually go and now so we actually want to create an instance of this model, and then we're going to set up our callback, train it, and review performance. So let's kick this off. Cool. So we've gone and created an instance of our fashion GAN class. So create instance of subclass model. And so what I've written is fashgan equals fashion GAN. So it's an instance of this big bad boy class over here. And then to that, what we're doing is we're passing through our generator and discriminator, because that is what our init method expects over here. Then we're going to compile it and pass through all of our losses and optimizers. So let's do that. And what order are they expected in? I think we can actually just copy these because we've named the variables the same. So GOP, DOP, GLOS, DLOS, GOP, DOP, GLOS. Yep, cool, we can do that. Cool, so that's compiled successfully. So fashgan.compile, and then we're going to pass through our generator optimizer, a discriminator optimizer, a GLOS, and our DLOS. Is this still zoomed in? Yeah, it is. Okay, that is that done. So that is step 4.1 now done. I know that took a while and there was quite a fair bit. We can get rid of that. That is our custom training loop and our subclass model now done. Now with the callback, I'm just going to copy this over from, because I've used this a bunch of times. And this is actually from, I think it's Francois Chollet's sample. I actually tweaked it a little bit just to get it to work, but I'm going to walk you through it. So we are going to import a bunch of dependencies. So import OS. So this just helps with folder navigation. And then we're going to import the array to image function. So from tensorflow.keras.preprocessing.image, import array to image. And then from tensorflow.keras.callbacks, import callback. So that allows us to create our own custom callback on epoch end. So if I go and import that, and then I'm not going to write this, but you can use this a ton of times for GANs. I'm just going to show you what you need to tweak. So this model monitor is going to allow us to save examples of our generated images as we're actually training. So there's two key parameters that you want to pass through to it: the number of images that you want to generate and how big our latent dimension should be. So remember that the latent dimension is just the random values that you're passing to your generator to generate a random image. Now on epoch end, it's going to go and do a bunch of stuff. So it's actually going to generate random values. It's going to pass that to our model generator, and then it's going to generate a bunch of images. Interesting that we're using uniform. Yeah, we could actually go and do that right up here, but for now I don't want to mess around with it. But I wonder, who knows, maybe we'll do that later on. Okay, so we're going and generating our images. We are then going and converting it to a NumPy array, and we're saving it. Now this is the important bit that I wanted to talk about. In terms of actually saving your images, you need to create a folder called images, and this is where these images are going to save to as part of this callback. So inside of your root folder, so this is the notebook that I'm currently working on, just create another folder called images. So it's literally new folder, call it images. And that is where your images will save to. If you wanted to save it somewhere else, let's say, for example, you wanted to call it GAN images. All you need to do is change the path or the folder that you want these to go into. In this case, I'm just going to save it into images because that's the way I've got it configured, but you could change that there. Again, all this code is going to be available, and this is optional. You don't need to go and use this callback. I've just found it a little bit easier when actually training our model. So I'm going to create that, and then we can train. So these two are really sort of optional, but they definitely help when monitoring your model. Okay, training. So we've now gone and created our subclass model, created our generator, discriminator. We've gone and created a callback. This is how we actually go and train. So here's equals fashgan dot train. Oh, actually, it's dot fit, not train. God, I'm falling asleep. And then we pass through our data set, because remember we created a data set, ds.asNumPy_iterator.next. So that is our data set. Let's take a look at the shape. So 128 by 28 by 28 by 1. So we pass through our data set, and then we specify the number of epochs that we want to train for. I recommend 2000. We're not going to train it for 2000 because it's going to take ages, but recommend 2000 epochs, which is going to take a long time. I won't doubt it. I'm not going to lie, it's going to take quite a fair bit of time. We'll probably train for 20, and then I'm going to give you the pre-trained model that you can use as well. If you want to use this callback, you don't have to, but if you wanted to use it, you can pass through callbacks and then pass through model monitor, which is the name of this callback over here. Cool. Alrighty, cross your fingers because we went and wrote that entire training loop without testing it. So there might be some errors. We'll actually see. So if I go and run this, we got an error already. All right, what's happening? Sequential object has no attribute trainable variables. So I'm pretty sure I've spelled that wrong, and you can see I definitely have. Where was this line kicking up? It was in DOP. Yeah, I thought I wrote it wrong. So trainable VAR. Nope, it's there. Yeah, so you can see I got an error there. So that's a typo. Copy this. It'll be that VARIABLES. Okay, let's run that again. Recreate our fashgan instance, recompile. Got another error. Got an unexpected word training. self.generator. Okay, we've closed that off incorrectly. That's fine. So that is here. So the reason that we're getting an error there is because we are effectively passing training equals true to this tf.random.normal. So you can see I'm missing a closing brackets there. That's better. Can remove that one there. Okay, so let's run that. Recompile. Let's try to fit now. It's looking more promising. There you go. We're now training. So what you should notice is that your D loss and your G loss sort of balance. They're not no one is going to blow out, or ideally you don't want one to blow out, and you don't want one to decrease really fast, and you don't want one to increase really fast. You want it to sort of kind of stay steady. And this is what you're kind of noticing here, right? So it's sort of bubbling around 68, 67, and likewise we're sort of getting that around for our G loss as well. It might increase occasionally, but ideally you want it to be stable over the longer term. So what we're going to do is we're going to let that train, and let's give it a second just to ensure that it generates some images. Because remember, it's going to generate an image on epoch end, which is dictated by this callback over here. So if I go into our images, you can see it was generated seconds ago. That is our initial image. It's literally just this random black square with little white bits on the corners. So nothing crazy at the moment, and this is common. So it'll suck for a ton of epochs, and then it'll get way better. So just keep that in mind. So you can see our generator's already spiking. Not spiking massively, but it's definitely increasing. So we'll let that go, and then what we'll do is we'll review model performance. I'll load up the pre-trained model, and I'll give you the ability to go and download that yourself, and then we'll go from there. We'll be back.
5 minutes later.
Alrighty, that is the beginnings of our GAN now trained. So if we actually take a look at the loss, you can see that the discriminator started to stabilize a lot more versus our generator starting to reduce in loss, which is a good sign. Perfectly okay. If you do run it for the full 2000, you'll see that they start to converge and they sort of reach this happy medium. So that is perfectly okay. As long as you're not getting like one blowing out, one going massively low. And so ideally you don't want, like what you don't want to see is one, like let's say for example, your discriminator is training and then it goes to 0.00001 loss and the generator spikes out of control. That is probably an indicator of mode collapse or the fact that just one of the training rates is way too high or low, and you got to stabilize it out. But for now, it looks like it's okay. And again, I'm going to give you the pre-trained models as well, the one that I went and trained for 2000 epochs, so you can test that out. But before we do that, let's quickly go and review performance, and then we'll jump back on over to our client. So because we saved our training inside of a variable called hist, we can access our performance. So if I type in hist.history, you can see we've got our discriminator loss, we've got our generator loss. So we can actually go and take a look at those. So let's actually create a plot. Perfect. Alrighty, so there you can see it. So what's happening is our discriminator has sort of steadied toward, let me zoom in on that. So our generator has spiked up, but you can see it's definitely coming back down. And this was pretty common. I saw this a ton of times. Keep in mind, we've only trained for 20 epochs, which is by no means the end state. You'd have to train for a ton longer to get a really, really good model. I think I actually did the full 2000 epochs. But you can see that our discriminators sort of bounced around down the bottom at 0.2 something. What did it actually have? 0.26 would seem to be about right. Now, our generator is coming down. So it means that our generator is learning how to generate real images, which is a good sign. So that is our training now done. You can obviously train for way longer and you will get much better performance as long as you don't see one of these spike up and the other spike down. Okay, that is looking good. Let's jump back on over to our client and then we're going to wrap this up by testing it all out. Oh, actually, wait, before we do that, we've also generated a ton of images, right? So we can actually take a look and see what this is looking like already. So it looks like we've got a bunch of white images. So again, pretty crap at the moment, which is why I'm probably going to show you the final train model. All right, so you can see we've got some dots. So let me zoom in. So you can see we're getting images, but right now they're white, which is a really poor indicator of performance. These are sucking. But again, as you train for way longer, you're going to start to get significantly better performance because you can see This is epoch 19, which is effectively epoch 20. It's starting to learn how to generate images right from the bottom. But that is literally how it starts. It takes a long time to get one of these fully trained up. I think I actually did spend the full 2000 epochs. Okay, let's go back to our client, have a chat, and then we'll go from there.
All that's left to do now is test it out. Sweet, let's do it. We can use the generator model to make predictions and visualize those tiny images using Matplotlib. To save you some time, I've also pre-trained a model that you can use, which will be available on GitHub, guys. Nice.
Alrighty, so now that we've gone and trained our model, let's actually go and test it out. So before loading up the pre-trained model, let's actually just test out with our baseline model. So we can actually load in weights for pre-trained models, and I'm going to give you those weights. I'll try to upload them on GitHub so you can test this out. First thing that we need to do is actually go and make predictions. So we can create a variable called images and use the generator, which is now trained through our subclass model. So generator.predict. We can use tf.random.normal and then pass through the number of images we want to generate. So let's generate like 16, pass through the latent variables, pass through 1, because that is the shape it is expecting. And that should generate images. Images. Perfect. So those are our images now generated. So you can see those there. Then the next thing that we can do is actually visualize them using Matplotlib. So rather than just looking at a random set of arrays, we can actually go and visualize them a little bit easier. So let's go and do that. Perfect. And that's what we're getting out of our generator. So pretty crap at the moment. But again, this has been trained for jack all time, 20 epochs, which is absolutely nothing. So let's actually take a look at what it would look like with a trained model. So one that's actually been trained for quite some time. So rather than using the base generator, what we'll do is we'll load up some weights. So I've got some weights sitting in a folder called archive. So I've got the discriminator weights and the generator weights. We don't need the discriminator weights. It's really just a training thing. But let's actually load up generator model.h5. So we can go generator.load weights, and we are going to go os.path.join archive, and then it should be generator model.h5. Perfect. So that looks like it's loaded them up. So if I go and run this line now, boom. So you can see we are now generating fashion. So again, exact same architecture. The only difference is I've gone and trained it for 2000 epochs. But you can see that by doing or running through this type of architecture, you can actually do quite a fair bit. Obviously, it takes a long time to train. So what I was typically doing is leaving my computer training overnight, or actually just spinning up a Colab instance with background execution, which I think you might need Colab Pro for, but honestly, it was pretty worth it considering that these take quite a fair bit of time to train. If you found better results by training in different architectures or better ways of training faster, do let me know. Let's actually make this a little bit smaller so we can see it. You can see that we are actually generating images of fashion. So we've got pants, we've got bags, we've got jumpers, we've got shoes. I don't know what that is. I think it might be a bag again. We can go and generate more images. So again, we've got like sort of sneakers now. I don't know, slightly different type of bag, slightly like a men's boot or something there, or a sandal. Let's go and generate more. But you can see that this is obviously super powerful. So like we've done it on fashion, but you could do it on just about anything. Obviously, keep in mind that training is going to be a big factor, and the amount of compute that you're going to need is going to be a huge factor. And you saw what our model performed like when we were training using the old baseline model and not a pre-trained one. But I will make these weights available to you via GitHub so you can actually test this out. But you've seen what the performance looks like once you've actually gone and trained a lot longer. So I think when I was training this, I actually managed to get the generator loss to pretty close to what the discriminator was. So I think it ended up balancing out at around 0.6 for each one of them. So it was bouncing around 0.6. So that's just an indicator of what you might need to get to in order to get something that actually produces images that look like this. Last thing that we want to do is, just in case we want to use this later on, if we wanted to, you could actually just save the model, and we can do that using generator.save, and then we can pass through. We can pass through whatever we want the name to be. So we'll call it generator.h5. We can save the discriminator as well. Discriminator.h5. Boom. So you can see if we go into our base model, we've now gone and saved the discriminator and the generator. That is this done in a nutshell. So again, we've gone and done a ton of stuff in terms of doing this. So first up, we imported and installed our dependencies. We went and visualized our images. And remember, these are our real images. You saw what our generated images look like below. We took a look at datasets, building a neural network, creating a generator. And you saw that effectively your generator is passing the outputs to your discriminator. We then went and built our discriminator, and then we built this monster training loop, which obviously takes quite a fair bit of effort. We took a look at the callback and training. And again, the length of time that we trained for is by no means long enough to actually get a great result. I'd recommend 2,000 epochs. We did 20, but time permitting, I've only got so much time to generate these tutorials. So I figured I'd at least try to get this out for you guys. And show you what a pre-trained model does look like, because I went and pre-trained this a ton of time ago. And that's what the end output looks like. So again, we can go and generate more fashion if we wanted to. And you can see we're generating a bunch of random and different types of images, which kind of pass off as fashion. You could even try to do this on colored images and see what those outputs look like. Let me know if you innovate. I'm always interested to see what you guys build. Thanks again for tuning in, guys. Peace.
Thanks so much for tuning in, guys. Hopefully you enjoyed this video. If you did, be sure to give it a big thumbs up, hit subscribe, and tick that bell and all that good stuff. Hopefully you enjoyed this video where we sort of went back to the old tutorial style where we're coding up from scratch, building up our models, and then testing them out in real time. Thanks again for tuning in, guys. Peace.
Okay, so neural network. So the first thing that we need to do is